Oh, I'm going to do automotive.
Yep, I'm going to introduce you. So we're going to start in about 3 or 4 minutes here with our speaker. But before that, one of the members of our board, Steve Kirchberger, has a short presentation to start us out.
Okay, hey, thanks everybody, and welcome. My name is Steve Kirchberger, and you know me locally as the Southern Minnesota section treasurer, but I also am involved in some other activities in IEEE, and in particular, the reason why I'm talking tonight is I'm the chair of the Region 4 Awards and Recognition Committee. So every year, Region 4, which is basically the Midwest of the United States, gathers nominations throughout the region, and then those are reviewed and assessed and awarded. And out of the 19 awards for 2024, is great that 4 of those awards landed in the Southern Minnesota section. So I just want to spend a minute. So this is the full group at the presentation ceremony that happened San Francisco area in late January. And the first award here is this Outstanding Student Branch Award. So this is Minnesota State University, right? That's over in Mankato, very active student branch. They're involved in the community, and they received the Student Branch Award for 2024. And then next is Dr. Puteri, and she is the student branch counselor for Minnesota State University in Mankato. So she's very active in keeping the students engaged and helping them not only stay connected to IEEE, but stay connected to the community. They hold an amazing job fair there every year. And then the next award is the Outstanding Student Award, and Nathaniel Menuda received that, and he is a student at Minnesota State University. So you can tell Minnesota State University is knocking it out of the ballpark and really doing a good job. But I also gotta say these are competitive in nature. And then I know how to pause this. Oops. Okay, the last one I have here is for Jonathan, and unfortunately he could not attend the presentation, and so the award made it back to Southern Minnesota section. And so I'm going to now ask Jonathan to come down and present him with his award. Come on here.
Thank you.
Good job. Yeah, congratulations, Jonathan. Well deserved. And then after the presentation this evening, there's some sweet treats for you all, and you can come down and congratulate Jonathan personally. Thank you.
All right, thank you, Steve. My name is Paul Dolan. I'm the vice chair of the local IEEE board here, and I'm pleased to introduce tonight's speaker, Dr. Nathan Huber, who is a medical imaging scientist passionate about using artificial intelligence to advance healthcare. His doctoral studies at Mayo Clinic Graduate School We're focused on developing deep learning frameworks for CT image enhancement. He then worked in industry as a systems scientist for GE and currently is a clinical scientist for Philips. This talk will review the contributions of Ray Solomonoff, one of the founding researchers of artificial intelligence. Please welcome Dr. Huber.
Thank you, everyone, for coming out. Great to be speaking with IEEE again. I think it was maybe 2 years ago that I came and I spoke about AI noise reduction for CT imaging. But hopefully today you find this talk interesting. It explores some of my hobbies, explores some of the history of artificial intelligence, and then gets into a little bit of the science of what I'm working on, or what I have worked on mostly. But again, origins of artificial intelligence. This is a picture of the Dartmouth conference attendees. It's not a large group, but it was kind of a rotating group. And as you'll find out, it was over the course of the summer, probably maybe a couple dozen premier researchers came and weighed in on what they thought artificial intelligence would become. But I'll start with a bit about me. So Nathan Huber, but this is my little family. Hannah Huber on the left, Hallie and Naomi is our 2 little girls. Just before this, they were walking in puddles outside, so there's no more snow anymore, but we like it without the snow. So I went to Mayo Grad School and was a biomedical engineering student. And as we found out, GE Healthcare, Philips Healthcare, but still working with Mayo Clinic in collaboration. So it's wonderful to be close to home. You'll see in the top right, maybe, foreshadowing what's to come, but a stamp of the Mayo brothers. Indeed, I am a philatelist. So I have a stamp collection of my own. And in 2024, me and my wife decided it was going to be year of the hobbies. So we were going to rekindle some hobbies. For her, it was writing, very productive. For me, I was like, I'm going to rekindle my stamp collection. So a lot has changed since when I was, 10 years old, stamp collecting. Now I'm, interested in artificial intelligence. So I'm like, okay, what can I purchase? Stamp collecting is just an excuse to purchase stamps online. So I was like, oh, let's see, maybe I'll, look at some of the major contributors to artificial intelligence and buy their stamps. So there's Alan Turing. But then we also have an example of subject matter artificial intelligence in the top right, very, futuristic, having humanoid robots and whatnot. And then in the bottom, this is a stamp from the Netherlands that is from 2021, which is the first stamp that was generated by artificial intelligence. So they used generative networks to create these stamps. I'm very amused by it because of how poorly they created their stamps. Again, in 2021, we were all just kind of being introduced to these technologies just a couple years later, and now you couldn't tell the difference between real stamps and AI generated stamps. So it's a very rapidly evolving field. But then I stumbled upon something in this, pursuit of stamps with artificial intelligence that I'm going to share with you today. And it kind of links back to the founding of artificial intelligence. So my talk will have 2 parts. Part 1 on Ray Solomonoff, Part 2 on data uncertainty in the age of AI. I'm going to mostly just say AI broadly as a term, but there's different classes of artificial intelligence that I'm sure you've heard about. So machine learning is a subset of artificial intelligence. Deep learning is a subset of machine learning. At a high level, all of them are just trying to use technology to mimic human capabilities. So again, when I was looking for AI stamps online, I stumbled upon an article written by Grace Solomonoff, and she is wife of Ray Solomonoff. And inside of the article, there was one example of an envelope that was sent to Ray during the Dartmouth conference. And I was like, that is so cool. And it had her correspondence. So I emailed her and I said, that is so cool that you have an example of that. And she was like, oh, I'm glad you think so. And she sent me like 10 more examples. What I've learned to find out is that Ray Solomonoff saved everything. And he has, without a doubt, the most complete picture of what was done at the Dartmouth conference. And a lot of the things that Grace has shared with me have never been shared with anyone else. And today I'll actually have some show and tell to hand out. So hopefully you enjoy that as well. So Ray Solomonoff, if you just do a Wikipedia search, you'll see that he is father of algorithmic probability. And you'll see that he is kind of the innovator of more statistical methods within AI and probabilistic methods within AI. And we'll kind of discuss some competing ideas to what he was proposing way back in the 1950s when he was doing this work. His parents, Julius and Sarah, moved from Russia to New York. That's where they met. And then they went to Cleveland, Ohio. That's where they had Ray in 1926. And from an early age, he loved math, science, and electronics. He went to high school and he became kind of infatuated with this idea of how can I make a general framework to solve all math problems? And kind of throughout his life, this kind of common theme of these questions, like how do scientists make theories? How can machines use data to solve problems? What does it mean to think? These are really, fundamental questions that he truly pursued his entire life. And I think he made a lot of progress. I'm going to also have a slide to his other love, which is science fiction. And I think this is really cool because, of course, science fiction always has those futuristic portrayals of, 50 years down the road, this is what life is going to be like. And we don't often get the satisfying link to, founder of AI was interested and influenced by science fiction. And so this is just kind of bridging two worlds. But again, he was reading things about automata theory, cybernetics, thinking machines. I went through one of these 1950s sci-fi journals, and a couple of the titles that you see is mechanical maids, artificial intelligence helping around the house. You see cybernetics, wanting to buy a brain. And so it's an advertisement for a machine that can do your basic computing. But anyway, I thought that was a very cool link. And as part of this, I'd like to send around a couple things that Grace shared with me that I'd like to share with you. Examples from Ray's, vast collection of documents linking his love of sci-fi to artificial intelligence. So just a moment. So what these are one of them is an advertisement that Ray shared. He was the president of the sci-fi club at his college. And so this is the Invisible Man, which he was advertising for. And notice it's not free admission, 50 cents to watch the sci-fi movie. And then there's another one there that's someone who is requesting to be part of the sci-fi club. So again, now we're talking about the mid-1940s. And so, there's of course the futuristic portrayals, but there's really solid progress being made. And so in 1945, the first programmable computer, ENIAC, was created, containing 18,000 vacuum tubes, many, many resistors and capacitors. And this was all developed here at the University of Pennsylvania. eventually it was struck by lightning in 1955 and it stopped working. But yeah, it's amazing how far science has come. And in the 1970s, Ray was making a computer on this little board here with a bunch of wires, but you didn't need all the vacuum tubes and whatnot already. So rapid progress in computing. And now I'll go into Ray's time at the University of Chicago. So he studied math, science, a couple of his professors, Rappaport, Carnap, Fermi. Fermi is probably the name that you may recognize from physics. Again, he was doing incredible work in nuclear physics, and this is immediately after World War. So, of course, he had a big influence on the creation of the atomic bomb. But Ray Solomonoff got his master's in physics in 1951. And here's just a couple examples of the books that he was reading at that time. Experience and Prediction, The Impact of Science on Society, The Logistical Syntax of Language. And that's exactly what I would expect someone who is creating AI to be reading at that time. Here's a quote from his roommate. When I first met Ray, he was sitting in an armchair surrounded by piles of manuscripts covered in symbolic logic, to which he was continuing to add at a furious rate. It was some time before I took the significance of all that. His girlfriend also was quoted saying that cybernetics had become his chief interest for the last 5 years. So it paints a picture of he was really dedicated to his work. And at this point, artificial intelligence was largely philosophy. And so, again, deep thinker. Next, I'm going to send around a couple examples that I think are extraordinarily cool. These are envelopes where Ray actually started doing his homework on. So on one side, on the left side here, it's hard to say exactly what he's doing, but it looks to me like he is doing somewhat of a convolution, a series notation or something like this. And then on the right, he's designing an amplifier. Again, I think we have probably a lot of electrical engineers in the house. So if you look at this and you can make sense of it more than I can, I'd love to talk to you afterwards. But again, you can just see the way his brain works and the way that he starts writing on these envelopes. All right, this brings us to 1955, and that's where things really start heating up. 1955 is when John McCarthy coins the term artificial intelligence. So he did this largely in motivation of a conference that he was organizing that ended up being in 1956. He intentionally picked this name because he wanted to make it neutral enough that it didn't pull from the previous areas of automata theory and cybernetics that had kind of, ingrained certain ideals, certain ways of thinking, ways of working. He wanted something that was new and didn't have, all the politics behind it. So that's why he called it artificial intelligence. On the right-hand side, you see an approach to artificial intelligence. What I think was amusing, and you'll see this kind of as a theme at the Dartmouth conference, there's a lot of notation debate. Like you think artificial intelligence is this, I think artificial intelligence is this. So again, he underlines throughout this the words that, people might feel like that's vocabulary they wouldn't necessarily use or something like that, up to debate. But you see here in point number 2, it looks like one of his goals for this conference is to try to find a problem that they can work on solving. So everyone's working on the same problem. That makes a lot of sense if you're trying to align everyone in the field. That sort of concept, propagated for years and years and years. And In the 90s, of course, people were still using AI to work on chess problems and other games. So that's kind of cool to see that starting in the 1950s. And then here's the invitation that Ray got from John McCarthy. And I'll just read it for you. You are one of the people we would like to invite to the summer research projects on artificial intelligence. The terms are $100, which will probably count as a fellowship and be tax-free, plus traveling expenses. And this was going to take place June to August in Hanover, New Hampshire, in parentheses, a cool place. So Marvin Minsky worked hand in hand with John McCarthy. Marvin Minsky met Ray at a conference. He liked him, and Minsky was the one who suggested Ray for attending this, esteemed conference. And a quote from Marvin Minsky: "It's come to my attention that Ray Solomonoff incessantly fills notebooks with observations of his and other people's ideas, to which he may or may not agree. I cannot begin to describe the extraordinary depth and completeness of these notes, on ground alone that he would be a great asset when it comes to writing a report of the project. If Ray is present, the bulk of the work will be done automatically." So again, and I think it's just so cool because it's just like so true to that note-taking quality, to also like the fact that he saved every letter that was ever sent to him. And that's why we can do like a cool presentation like we can today. 1956, the actual Dartmouth conference happened. And there's only 3 individuals that were there for every day of the conference, and that is John McCarthy, Marvin Minsky, and Ray Solomonoff. But then, of course, there was partial attendance by all of these other figures, and I'm not going to go into a lot of depth, but each of them ended up being, founder of this, founder of that. They each pursued their individual ideas, and it's really cool to see how artificial intelligence just took off after this conference. So I don't have these letters, of course, to share with you today, but I think the coolest letters and the one that kind of, spurred me to reach out to Grace are the ones that have that postmark of 1956, summer of 1956. Again, these, landed on Ray's doorstep while he was there at the conference, and I just think that's extraordinarily cool. The first letter on the top left, you can see it's a June postmark. And that is significant because some people argued that the conference actually didn't start until July. But here we have evidence that it did indeed start in June. So I think Ray, Marvin Minsky, and John McCarthy probably started a little early. Most of the other attendees probably started in July. Down here in the bottom right, I think this is kind of a funny envelope because it was clearly sent to his home address in New York, but then they crossed it out, resent it to Dartmouth because, of course, he was not home that summer. And then this is the coolest letter of all, and this is the one that I had contacted Grace about. Ray Solomonoff, and then you see there in the line, Symposium on Synthetic Intelligence. And I think this is just so cool because probably the most well-known attribute of the Dartmouth conference is that they aligned on artificial intelligence being what this field should be called. And this clearly shows, the word hadn't gotten out yet. This person wanted to call it synthetic intelligence. We don't hear about synthetic intelligence much anymore. So I just thought that was very, very cool. And then this final letter, this is sent from his parents. It's sent from, you can see Cleveland, Ohio there. I look up their home address. Unfortunately, now it's in Orange Theory, so a fitness center. But this is indeed where Ray Solomonoff grew up. So I don't have any of those very, very cool covers that occurred during the conference, but Grace was kind enough to send me the September 1956, so immediately after the conference, and I'll send that around. So the letter that's included inside of this envelope starts with, "I hope you enjoyed your summer research project." I think it's safe to say he did. Okay, so what was the Dartmouth conference like? They had the entire top floor of the Dartmouth math department to themselves, and they would meet every week. They would rotate about who was leading the lecture. And then they would just kind of go at it. They would debate, they would talk, you know, they all described it as a very, very fun and intellectual experience. I'm gonna just comment on a couple examples. So Trencard, he discussed what it would be like to have checkers be their project that they worked on for artificial intelligence. And he talked about how there was different board positions and how you had intermediate goals in checkers and how you would kind of encode that into a computer problem. And then we have Bernstein, who talked about chess, complaining or describing how you have ideas about how to play. You have half the time spent on evaluating positions, half the time spent on updating the positions. And he was just kind of talking about, from a chess player's perspective, what sort of intelligence they're going through. Then the final thing that I wanted to point out is, I thought this was hilarious. One afternoon, they decided that they wanted to align on what heuristic meant. And so happened to be a dictionary sitting in the corner of the room. And so they go to the dictionary and they open it up, look at what it means. But the amazing thing is that when they went back to visit, home base, with 50 years later, that dictionary was still in the same room, opened up to the exact same page. Nobody had used that dictionary for 50 years. All right, and then 3 things that people have kind of pulled out of the Dartmouth conference as important contributions. I think they talked about a lot of things that probably didn't end up being, what we consider artificial intelligence today. But these 3 things, you can see the thread to what we currently consider artificial intelligence. So semantic, numerical, and symbolic information. So they really considered a new paradigm of encoding intelligence as symbolic information. This is different from earlier methods that were focused on brain modeling. And this is certainly something that we see, of course, everything is programmatically encoded now. That really kind of originated here at Dartmouth, or at the Dartmouth conference. Then we have number 2, which is deep versus shallow methods, which of course, from that first picture, we have, various flavors of artificial intelligence, deep methods. Now we consider it as very big data sets focused on maybe very specific problems, or, using all that data to make very advanced decisions. Back then, they kind of described it as limited domain projects versus more general projects. And so limited domain means I created a program that was really good at checkers, whereas general intelligence might be something more, understanding how a human would approach whatever problem they're given. And then 3, deductive logic versus probabilistic methods. And this is kind of a key point for Ray, because of the group, he was most determined to get across this idea of probabilistic methods. Oh yeah, go right ahead.
Yeah, if I can interrupt.
Yeah.
Would a large language model be considered deep or shallow?
I would consider it deep.
That's not like a specific task of predict the next word.
Oh, that's a good question. Yeah, well, so it's definitely categorized under deep learning, but I understand like your idea, like it's very focused problem. But it's getting broader and broader all the time. So I guess a lot of these things are, it's not well defined. So I don't know exactly how to answer you, but it's a good question. Indeed. So Ray, father of, algorithmic probability, was really determined to get across that, artificial intelligence should look at prior data and then infer what it thinks is the best outcome given what it knows from prior data. There was another line of thought that if we just trained enough deductive reasoning, we know this is true, we know this is true, and then apply those two together to get this is definitely true. If we just have enough rules, we can solve a chess game. Indeed, both deductive and probabilistic methods are important, and we've seen both of them have a lot of success. But going back to large language models, these are a classic example of definitely a probabilistic approach here, where computers are fed so many lines of just general text, and then they're able to learn to infer what someone is meaning by any given string of text. So this is indeed what Ray Solomonoff was always kind of pointing towards, and I think, of course, has become a very important part of artificial intelligence. And then I'd like to just include this slide of many pictures of Ray. I think he was just a phenomenally interesting individual, had a lot of fun, very close to family, of course. In the bottom left, you can see the logo for his AI company, Oxbridge Research. Again, quite a character. Okay, so if we're considering probabilistic AI, I think a natural question is, what does uncertainty mean inside of AI? And this kind of feeds into something that I was very curious about, especially in grad school. What is the uncertainty in AI predictions? So a little background, AI has been used for medical imaging, pretty much all areas of medical imaging at this point. We see an example here of image processing. So on the top right might be an image that you'd see before AI reconstruction. On the bottom, after AI reconstruction. So you can see that granular texture that's on top of the liver in this case is removed so that the radiologist can look at this and see, oh, it's much easier to see where the lesion is, for example. But every single step of the process, when the patient list comes in, positioned, they're scanned, they're triaged or whatever, every single element of that has, dedicated AI models that have been considered or being developed or being deployed at this point. But I think something that doesn't often get discussed is, what about data uncertainty? And so this is a question that I had about halfway through my grad school experience. I sat back and I was like, okay, I'm going to compare beautiful images. But what is the uncertainty in those images? Every radiologist would look at it and they would say, oh, this is much nicer. But they can't appreciate from looking at the image alone what the uncertainty is in that image. And I kind of went back to, in college, when I was a chem student, and we would always have to calculate the propagation of errors. Like that was just, step one of analytical chemistry is learning how to do error propagation. But yet I had never seen a medical image with errors attached to it. even though we know intuitively that there is error attached to it. So here's an example of a denoised medical image, and you can see that there's a lesion in that bone. You can see in the cortical bone, there's a gap. But what you don't appreciate is where the data came from to create that image. And again, this is a very, very low dose, 10% dose. You can see in the noisy image, that's that granular texture again, in the middle, that, oh, now I'm a lot less sure that there's a fracture in that bone. And then you can look at the 100% dose and you can now be reassured that there's actually no fracture in that bone. And this is indeed propagation of errors by AI. So this is just a very concrete example, but as you get to smaller and smaller lesions, you can imagine this happening more and more often. It's hard to know, is the AI performing well, or is there even enough statistical evidence for it to make a judgment call on this data? So here's another example of grad school work where we had a cadaver that we scanned 100 times. And I applied my AI denoising to one example of the image, and it worked excellently. And I think everyone can appreciate that the texture is removed. There's no obvious loss of data from it, and it looks way better. But I was absolutely blown away when I looked at the ensemble average of those 100 repetitions, how much information there was in that image that I just had no idea, because it was completely drowned out by noise. So you look at the cortical bone or the trabecular bone here, and you see so many fine bone structures. And then you look at the muscle in the back here, so many like different grooves in the side of the muscles that was completely drowned out from the regular image. So indeed, there is uncertainty here in these images. So if we had a way to understand that uncertainty, quantify it, communicate that, there's an opportunity for physicians to do a better job in their diagnosis. So I'll discuss some terminology. We have dispersion or variance, which is defined as the variability in the expected AI output. You also have the bias, which is defined as a systematic difference between the AI output and the actual value. And you can see a little chart here. You know, if you have low bias and low dispersion, that's ideal. You're right on the target. If you have a high bias but low dispersion, you know, all your arrows are missing the target in the exact same way. If you have a high dispersion, now you're, you know, all over the place. And you can have any combination of those in your data. There's also two terms, aleatoric uncertainty and epistemic uncertainty, and these are describing different types of uncertainty. Aleatoric is referring to the actual underlying data being processed, and the fact, like I've been describing, if your data is imperfect, you will propagate that error, and then you'll have an imperfect answer from that output of your AI. Epistemic uncertainty is associated with the AI model itself, and it has to do with the random initialization of weights and the training process. So I kind of dug a little deeper and kind of developed a couple different ways that I could look at uncertainty a little bit more in my processing. And so approach number one is the simulated perturbation assessment. And so what I did here is I took the image and I put little known blips in the image, and I made them big, I made them small, I made them high contrast, I made them low contrast, and then I plotted like signal retention based on all these different parameters. And this was a kind of a nice way that I could characterize my network's performance. You can see that something like the head CTA had very low background noise, but it was able to detect these perturbations really well. Whereas in the lung screening case, I had a tough time detecting a lot of these perturbations, especially the negative going ones, and that just has to do with the nature of the data being processed. So that's one way I kind of dug into the models deeper. And then the second way I I looked into it is this bootstrap simulation approach. And so again, I had one AI network that was processing one image. And I was like, what if I simulated 100 images and I applied my network to each of those images, got a slightly different answer, and then I examined how those slightly different answers impacted in terms of dispersion and bias. And so you can see how I did that a little bit from this flow chart. But from the output, you can see that again, any one CNN denoised image looks great. But if you look at the dispersion map and the bias map, if you look over multiple iterations of the same thing, processing on different data, you have around 50 Hounsfield units, which is a non-negligible amount of error for a clinical diagnosis. And then I was like, okay, now that I have this bias map, intuitively, you're like, okay, maybe I'll just add that bias back into the image and make it better. So I did that. I added the bias back in, and it does look sharper. But what I quickly found out is that, any error also is amplified by using this approach. And so you got to be very specific and when you would want to use it. And maybe something like trying to detect a bone fracture or something like that, it would be a good application. But something like in the bottom where you're looking at soft tissue and minor fluctuations in the data matter, it's probably not as good of an application. So as with anything, there's kind of a finesse with the image processing. So I guess I'm coming to the end of my talk now, and I wanted to point out a few things that I kind of took away from all of this, hobby exploration, scientific exploration, and whatnot. So first of all, appreciating the people behind AI. I think it matters. I think oftentimes you look at the news headlines and they talk about, technology advancing at an alarming rate, or, this model is capable of XYZ. And they really kind of removed the human that developed it, the human that tested it, the human that's, implementing it. And they make it very, artificial. And perhaps it's because the people like thinking that it's artificial. But I think it also shoots us in the foot because there's a very high amount of distrust around AI. And I think this kind of stems from dehumanizing it. So appreciating the people behind AI like Ray Solomonoff, I think it's important. Then I wanted to just point out algorithmic probability and uncertainty matters. So I think, like as you are exposed to AI technologies, kind of understanding when they're going to work, when they're not going to work, and perhaps, advocating for people to understand and be more explicit about the uncertainty they make in the predictions that they show you. Then, more specifically to medical imaging, I feel like we need better handling of uncertainty in medical images. Again, medical images have inherent uncertainty. Some of that can be quantified. Like when we have these post-processing tools that we use, we can and should quantify the amount of error that they're introducing into our data or the way that they're propagating error. And I think that information is going to be very key in future iterations of medical imaging to advancing diagnosis and specifically making sure that you're making the right diagnosis and not giving incorrect diagnosis. And then finally, pursue your hobbies. And I'd like to think that Ray Solomonoff pursued his sci-fi hobby and it led him to be a great innovator in AI. And in my case, I pursued my hobby of stamp collecting. And lo and behold, now I'm speaking to you tonight. So it was a joy talking to all of you. Thank you so much. I'd be very happy to answer any questions you have.
So do they specify the uncertainty in the medical imaging, and do people look at it if they do?
They do not. They have approaches to reduce the impact of uncertainty, I would say. Like they'll make a diagnosis based on data in like, prior evidence. We think that this is a lesion because of, it looks like a lesion. So I think this all is indirect ways of incorporating uncertainty. But I think in the future of medical imaging, you talk to a lot of physicians who feel quantitative imaging is the future of medical imaging and being more data-driven in diagnosis, for example. And if we're going to make that leap to more data-driven diagnosis, understanding the uncertainty is critical. Yeah. And we don't have methods even developed to do that sort of calculation right now. Yeah. Go right ahead.
Excuse me, what level or qualification is the audience for these images? Who are they intended to be placed in front of?
Yeah, so radiologists and radiologists pursue a medical degree and then specialize within their radiology field. So many, many years of training. And I guess one thing of relevance to note is a lot of the AI technologies that are being used were not available during their training. And so, first of all, they have to be adaptable, looking at images that are entirely different than they might have seen during their training. Yes, go right ahead.
I don't want to belabor this, but I had my business for quite a few years has been implementing what other people asked me to do with a microprocessor, where I didn't have an opinion on what they were asking me to do. They just tell me what they wanted and I'd give it back to them. And one of those was image enhancement for radiology. This was like quite a few years ago.
Amazing.
And the person who wanted to do it was not a radiologist. They were manufacturers of the X-ray machines, and we implemented a very simple approach to what you've done here, and that's when they finally got radiologists involved in it, and the project died instantly because their reaction was, my whole specialty is understanding all the subtle image differences in this image and the gradings. This is analog. This is pure chemical, photographic X-rays.
Yeah.
Digital stuff here.
Yeah.
And we were using digital techniques, and they said, you're taking away the very information that I spent half my life learning to interpret. And they definitely were not interested in it at all. And if they'd have gotten the radiologist involved earlier, there'd have never been the project.
Oh, wow. Wow.
Now, there was nobody at
That's
that
a great
time heard of
example.
AI, heard of artificial intelligence. I mean, we were talking machine adaptation, just like the contrast control on your video set. So very primitive.
Oh, wow. That's very cool.
Well, it wasn't at the time. That's what I'm trying to figure out is how this changed so much. That was probably 25 years ago.
Yeah, no, that's a good question. So I think going back to kind of that first slide where we described artificial intelligence to deep learning. So a big pivot that has occurred in recent years is that we used to kind of prescribe the features that we thought were important for the model to make a prediction on. So you might look at it and you might say, this is the liver, this is this bright, this is bone, this is this bright, and then apply some, model that a human kind of picked some features that were important and prescribed them. A big pivot has been, in the deep learning age where it's now like entirely data driven. So you provide, thousands or millions of examples of the transformation that you want it to achieve. And then you give it full autonomy to choose what features are important to the data and how to make that transformation. And so it's just been like, instead of having something that has been perceived poorly by radiologists, they look at these images and they are, in some cases tricked into believing that, a 50% dose image is indeed a 100% dose image because the image processing is so good on that image. And that's to great benefit of the patients. I mean, we're talking about reducing radiation dose, which of course is, always a priority in medical imaging. All
I
right.
have a couple of technical questions. Could you go back to your the noise removal
Mhm.
slides? Yeah, here. Okay. So number one question is, how did you define the noise?
Mhm. So what I did here is I used a deep learning algorithm trained on hundreds of examples and processed that first case in the first column. And you can see that there's kind of that granular texture on top of it. And that granular texture is what we call noise in imaging. And the output of the algorithm was the second column. Input image and the output image, then you have this noise image, and that's what it removed. And you can see that it is all that granular texture.
Did you study the noise, areas just away from the, the interesting area?
Um,
For example, the first column,
mhm.
like the top one, you have, the something's at the center, right?
Yeah.
Then you want to find what is the noise. Then you go to the, the four corners and take four corners image. And then here, maybe the noise, is that right or not? Maybe too simple.
No, I think you're piecing apart the problem in a great way. Yeah, I think we can talk more afterwards, but I didn't study the noise that much. What I'm looking for in the noise is that I don't want to see a bone in the noise. Like if
Right.
I saw a bone in the noise image, that means I took something away.
That's right.
But if I don't see anything except for random texture, that means I did a good job. But what's really cool is even though from my perception I did a great job, I look at this ensemble average, and this is evidence to me that in that noise, there's a lot of signal that I removed. Whether or not it's going to change the patient's diagnosis, probably not. Hopefully not. But it is important to know that, the imperfections of what we're working with.
So the second one, follow these ones. The image you use is the processed image or the raw data from the machine?
Okay, so the first column would be the what the image comes from, like from the scanner. The second one is what it comes from, like my computer, where I deploy my model. And then the final one on the far right is what you would never actually achieve in a patient exam because it's 100 times the dose that a patient would get. But again, this is a cadaver study, so we were able to have that perfect ground truth.
Sorry, actually, what I meant is first column.
Oh, yeah.
You asked what? Okay, last one is how much time you need, from the first column to get second column for each frame.
It's a good question. I would say seconds. It doesn't take too long. Usually they're batched into like a whole entire series of hundreds or thousands of images, and that will take a few minutes or something like that.
So that is the things. When you say to get the second column image, you need to study like hundreds images, right? Is that image is from the image bank or from the the current scan image?
Yeah, so this is only one image that it generated it from. When it was trained, so there's kind of two phases. There's the training phase of an AI algorithm where you give it as much data as you have available to you. And then you transition from the training phase, and now the model stays the same, and it's applied to new data that it's never seen before. And so this is an example of just one new data that it's never seen before.
So based on your theory, when you do the training, that means, aim for, actually the training is for the specific machine, right? Not for somebody or.
Yep.
the family members.
Yes.
That's what I said.
Yeah. That's right. Yep.
Thank you.
Yeah, thank you.
If you look at column number 3 long enough, you can kind of see what I maybe am incorrectly calling some strange attractors in there, some almost sub patterns.
Yeah. Yeah, I think it is really interesting that the noise properties
The
of
noise only.
Yeah.
of CT imaging particularly, they have ideals within noise. Even the radiologist, like, they like some noise, but then if it's a different texture, they don't like it. And it all has to do with how much it obscures their view of the underlying disease or anatomy. So yeah, like you say, that texture is some product of the reconstruction process, and it's how you create images from X-rays.
But is it possible that there's some structure in that noise image that you're not picking up?
Yeah.
And are there way, have you thought about processing the noise image to make sure that it's or unstructured or whatever?
Yeah, I think I've thought a little bit about that. I think it's a good approach, looking at the noise to make sure that there's, not obvious signal loss or something like that. In most cases, it's more of just like, something that never is seen by the radiologist. It's just something that we generate in the back end. And then if we're looking at like the algorithm's performance, we might take a peek at it to make sure that it's working the way we think it is. But yeah, it's a good idea.
Any other questions?
Or just an idea,
Mm-hmm.
but if you can add your own randomly generated noise to the input before doing the CNN denoising, can you just add 100 or 1,000 different noise fields each time, and then look at the correlation maps between the different noise only images?
Yeah.
Have you done that?
Yeah, I mean, it's an interesting idea. I guess the closest thing I've done to it is the ensemble method that I described here, where we do like multiple noise insertions, looked at the dispersion and the bias in the network from this like bootstrap ensemble approach. You could look at the correlations in the noise. I think you might not find out more than if you just looked at the noise texture. But
I was more just thinking of it as a method to see the noise texture, because you could get rid of the non-texture bit.
Yeah, it's a good idea. Endless things to pursue. Thank you so much for coming out to listen.